Good morning, everyone. First, I'd like to thank the technical committee for the invitation to be here presenting the work that our group are developing at the Federal University of Technology, Paraná. The title of my presentation is Advanced Distributed Optical Fiber Sensing Technologies for Energy Systems. We are working with some companies in Brazil, and the idea is to present some results related to these projects, R&D projects, with oil and gas industry and smart and also dam and so different applications. Just a few words about our group, the Sensing Technology Group. Here are the leaders. Maybe you know some names here, but the most important here is the multidisciplinarity associated with this in our group, the photonics, advanced signal processing, instruments and measurements. And this multidisciplinarity is really important to develop distributed optical fiber sensors. Here are our team. Of course, the students, the laser point. It's not working. No. Okay, no, don't worry. Okay, thank you. Here is the students that we have in our group at this moment, the most important in our group, the students. Some numbers relate to the projects with different agencies. In Brazil, we have agencies regulating the areas such as electrical, petroleum, and transportation. Some numbers relate to patents, filed and granted. These patents are related to the projects with the industry. One startup, a spin-off incubated at UTFPR, the Immermessen sensors, and some numbers associated with certified students and scientific production. Our interests go from heavy industry and energy sector to biomedical engineering and robotic systems. Well, our motivation to develop the distributed optical fiber sensors are first, to get intellectual independence over distributed optical fiber sensing technology. This is important for us, but mainly for Petrobras, the main company invested in our group, to get knowledge of technology and implementation challenges. As you can see in these pictures, there are so many, mainly in the oil and gas, the offshore applications due to the harsh environment and the complexity associated with this environment and structure, and also in dam applications due to the size, the complexity to install the optical cables, and so many other challenges associated with these applications. And the development of a distributed acoustic and temperature sensing system for application offshore wells and dam safety. At this moment are the most important research or applications that we have in our group. Well, here is the timeline with some important milestones. We start the use of this technology with the distributed temperature sensing applied in power generators in 2012, after more than 10 years of experience in fiber optic sensors. In 2015, we signed the first project with Petrobras to know and develop the distributed acoustic sensing. And as you can see, we have some important results, and in 2021, we incubated the spin-off, the Immermessen sensors, motivated by Petrobras to transfer the technology to the industry. And in 2022, we signed another important project with CPFL to apply DOFS in dam. And in 2023, we start as a member of CIFON. CIFON is the International Joint Industry Forum aimed at promoting the growth of fiber optic monitoring system installations in the upstream oil and gas industry. This was very important for us because now we have a forum to discuss with big players discussing about the distributed optical fiber sensors. And more recently, some important results in offshore applications, whale record and also seabed seismic analysis. Well, but how does DOFS work? The principle is quite simple. The technology is not so complicated when we look to the components that we have in this system. And the principle is based on scattering of light on the fiber. We have different kinds of scatter associated with some phenomena, but in our case, we are interested in Rayleigh scattering. When I launch a pulse laser in the fiber, I have some scatter associated with inhomogeneities in the medium, in this case, the glass inhomogeneities. And I believe that most of you know OTDR, and in the case of a pulse laser, when it is coupled into the fiber on the test, the back reflected signal goes to the receiver with some information. In the case of OTDR, the loss, the attenuation of the fiber associated with the attenuation, the splices, connectors, and so on. This is because, as I know the speed of light on the fiber associated with the medium, I can also associate with the position of each event because the time, the flight time of the pulse in the fiber. If I have a good light source with good coherence, I also can measure other parameters associated with the amplitude, frequency, wave number, and phase. But for this, I need a coherent light source. In the case of the OTDR, we have a no coherent light source, and then I don't have so much information about as we have using a coherent light source, a narrow line width. As you can see in the right, I have a lot of information associated with the interaction of the light with the medium due to the inhomogeneities on the glasses. Here is the topology of our DOFS. As I told you, it's not so many devices associated with this system. But of course, there are some important parts here that need to be considered. The first is the laser. We need a really good laser with narrow line width laser with a good coherence to develop the DOFS. And in this case, we have the most part of the light is modulated by acoustic optical modulator. It adds a delta F, a component in frequency associated with this modulation that is amplified and launched to the fiber on the test after an optical circulator. The backscatter signal is beaten with a local oscillator, a small fraction of the light from the laser, and then I have a bandpass filter with the same frequency that was generated by the acoustic optical modulator. And then I can process the signal. Here, the equation in the left, I can see the electric field of the local reference light wave. And here, just to reinforce the importance of this laser, the main parameter is the laser phase noise, and this is really important when you choose the laser for DOFS. And here in blue, the electrical field of the Rayleigh backscattering light wave, where we have some important parameters associated with the shape form, the main frequencies, the phase of the incident light, and the most important, the phase of the ITH scatterer, where I have the information of interest. After the balance for detectors, I have the current associated with the signal. And again, the resulting phase is where I have the external disturbance associated with temperature gradient and acoustic strain. Then the DOFS is sensitive to temperature and strain. To prove this, we have an experiment here where the idea is to study not just the temperature influence, but also the low frequency. Because we have some projects with seismic analysis with low frequency, it is important to study this kind of signal in low frequency. And as you can see here, the Rayleigh scattering has a temperature dependence. The OTDR-based TGS is cross-sensitive to both phenomena, strain and temperature. And as you can see in the graph, it's a good correlation between the temperature reference and the phase variation measured by the DOFS. And here are some characteristics of our DOFS. It's a real-time acoustic and temperature gradient measurement simultaneously. It has a linear response, high sensitive and low noise, and fully configurable acquisition parameters. And this is really important in different applications, as I will show you. We can use in different applications, seismic, flow pattern, multi-phase flow analysis, and others. Then, moving to the applications, here is the facility that we use. It's a laboratory in our university, the Multi-Phase Flow Research Center in Wayne. It's a mechanical department, and then we use this facility to study a little more about multi-phase flow with DOFS. In this plant, we have the gas as air and liquid water to measure phase velocities that are independently controlled, promoting a controlled flow patterns, and this is really important as a reference for us. Well, this application, we use DOFS to leak detection. We coil the fibers around a pipe, and in a specific position, we use a driller and to make a small rule. And as you can see here, we have we have some results, the regular flow. As you can see, it's important to see a pattern associated with the flow, and then we start drilling, and then we add some new frequencies, and here start the leaking. And it's possible to see a good pattern associated with each event. Another way to see is based on the frequency, in the frequency analysis, and then here in the y-axis I have the frequency and the time, and the drilling, we have a specific frequency, 120 hertz, the air leakage during the leaks, and the slug latency with the low frequency associated with this event. And the right, I can see also the temperature variation associated with the leak. It's important, we use 3 different lengths on the pipe, and as you can see in the lengths of 26 and 58 meters, we don't have any change in temperature, and in 37 meter, where is the rule, I can see a small temperature variation, about 4 degrees. And another application in partnership with immersion sensors in a project with financial support by Petrobras, we use this system to steam leak detection and characterization in a refinery in Brazil, where the idea is to have a system to detect, locate, and quantify the steam leakages with good spatial and temporal to construct spatial and temporal maps of leaks along the pipe. That is possible to have an historic records of the leak events and estimate the resource cost spent on the leaks. We instrumented 300 meters in a pipe hack in this refinery, And to do this, of course, is really complicated because there are lots of pipes, some of them out of work, and the idea was to develop a system, no intrusive, and then we develop a special sensor that you can see here in this picture in a specific position. Is an optical microphone, and the idea is to listen the sound associated with the steam leak, okay? It's a movie with, as you can see here in these points, I have some leaks. The coast, just a minute to, yes, here. And with this system, I can estimate the cost because I know the energy loss, the steam leak, and the total events. And this is an important tool to the refinery to estimate and to define the time to maintenance. This is the optical microphone that we developed. It's a quite simple idea. We use a membrane, and surround this membrane we have a coil optical fiber, and this membrane improves the sensibility of the DAS to listen, to record sounds associated with the leak. And we have a patent on the optical microphone for using distributed optical fiber sensing system. The idea is to reconstruct the acoustic space through a non-intrusive monitoring. It is completely passive, no power or communication required, suitable for hazard areas, as you can see in this picture also. Again, imagine to pass cable through the total pipes is completely impossible. Then the idea is to listen, to correlate the sounds in the events. Some characteristics of this device is it has a linear response, as you can see, a broadband frequency response, and it's possible to multiplex a lot of microphone in a same cable. And here is the audio that we recover using this device. We don't use any special algorithms, audio algorithms, okay? It's just the sound. We have some works associated with the study of optical cables to apply in seismic. And in this, we have a trench which is approximately 50 meters long. And then, as you can see here, we use just one cable in one direction, and then it comes back. And then I have some movements, and we record just it's the same cable, okay, but in different directions. And here we have a movement, a person running, moving away, jumping in a specific point of the cable, the region of the cable, and running, approaching, okay? And again. That's a little, okay, and jumping. And running, approaching. What is important here is to know that we can measure more than time domain or color map. You have a lot of information in the signal, and then we can distinguish each one. Some results for glass field and small scale dam. We have a good space to do some experiments related to seismic, and the idea was to compare the DAS and the gel phone for seismic application. In this arrangement, we use 100 meters of optical cable and 24 gel phones spaced by 2 meters. This space is important because define the resolution of the analysis, and then we use a active source, which is a sledgehammer, hit against a metal plate, and the gel phone is really near to the cable in this experiment. Here we have some details about the technique. We use the MASW. It's very new for geophysics, but with the gel phone, and we compare in the same place, the same experiment, DOFS and gel phone, but it's important to say that gel phone is a point sensor in a triaxial analysis. In the optical cable, we have a direction mainly well defined on the fiber, and then we are comparing different systems, okay? It's important. And the idea is the DOS signals are discretized into virtual channels aligned with the spatial position of the gel phones for direct comparison, okay? And here we have the time signal acquisition, then I have the time and the position along the experiment. If I have the time, if I have the distance, I can invert the velocity, and also I have some frequencies that I can measure, and then I have the dispersion curve. This is the most important for geophysics, because from this curve they can identify some frequencies and velocities, and of course the materials in the soil. And then I can inversion curve with the depth and the velocity in one specific region. And in this experiment is the middle of the arrangement. If I want more, I need to move the arrangement, and we did. Here is some details about the DOS processing. As I said, I need to compare the DOS with the gel phone. The systems are different, and then I need to follow this sequence to determine the signal that can be compared with the gel phone. We use a standard acquisition at 10 kilohertz with a downsampling to 1 kilohertz. This is really important to avoid unwrapping. It's a manner to reduce this problem associated with the DOS. We have a special resolution about 2 meters. And another important thing to know is that in this kind of analysis, in seismic analysis, or mainly in multi-phase flow analysis, the FK filter is a good tool, and it's very important to understand how these work, because this filter is really important in many applications. Again, some comparisons between DOS and gel phones. As you can see, the signal noise ratio is very good. The signal is very similar, and mainly, as I said, also these curves are very similar. We need to improve in some frequencies, mainly in 10 and 30 hertz, but the results are really good. And from this analysis, I can reconstruct a map of the soil. The total length, or the depth, is associated with the length of the arrangement. As I show you before, we analyzed 48 meters of the arrangement, okay? And then I have here the depth, about 25, 24 meters, but DOS and gel phone has a really good similarity. As you can see here, we can see a big variation between these layers in 15 meters deep, and the characteristic of the soil, a soft soil, and maybe rocks, I don't know, but in here is the velocity. The colors is associated with the velocity of the medium, okay? Okay, quick. Okay, we have the same in a small dam, an experimental dam, and as you can see here, I can define the different layers: concrete, stone, gravel, pebble, and also the soil. Here is a challenge because the big rocks I have spaces, air spaces, and it's difficult to propagate the mechanical wave in this environment, but as you can see here, we could measure again. And here, the most important for us, the most important results in our group at this moment was to record whale vocalizations. We use a cable in the ocean linking the unit, the monitoring unit and the production unit of Petrobras, and we know in this place there are whales during a specific month, and because they have some measurements before, between 2003 to 2012, and the yellow points are whales, and during 3 days, the end of the year, we record these signals. Here you can see the V-shapes associated with the whales, and we can distinguish between the individuals because in one is higher pitch sounds and another lower sounds, and again, we can also record the sound associated with the animal. Okay, and here we believe that there was a boat here because the signal is very clear, but okay. Conclusions, as a member of CIFON, we expect to learn more about the challenges that the community is facing, continuous search for improvement and performance of DAS, DTS, and the TGS, both in measurement quality and distance range. And this time we are very work hard to improve this. And the field, of course, to improve our field tests with relevant laboratory setups and field surveys. Okay, I like to thank these companies that invest in our group, and of course the government agency. Thank you very much, and sorry about the time.
Thank you very much, Giancarlo, for your talk. And now we have 2 to 5 minutes more or less to interact with the speaker.
Well, thank you for the excellent talk, very nice talk. Well, I have like very specific technical questions that maybe is better that we discuss in some other time, one-on-one. But I want to ask you like a very general question, because I think that your group is in a unique position, a very interesting profile, because you have experience both in the hardware, in developing your interrogators, but at the same time you have a wide range of experiences in the applications. So my question is, what is harder in a way? What is the problem? Where is the bottleneck now in the actual use of DAS particularly? Is the applications demand more performance, more sensitivity, more resolution, or the harder part is actually the signal processing, the developing machine learning for specific applications? So what are your thoughts on that?
Okay.
Thank you.
Thank you for the question, Alain. In this application, for example, the challenge is the size of the data associated with this measure. 46 terabyte to process, to find whales. And this is really complicated. This is really a challenge. Then we need to use machine learning and many tools associated with strong algorithms to distinguish between the signals. For example, a boat, we believe it's a boat, and whales, and so many other noise. But In this case, it's not so much noise because it's the water, but we have boats, we have other animals and movement of the water, and but the main challenge, in my opinion, is the algorithm to process this signal. This is a big challenge. We have a joke that we need is not quantify in terabyte, but in kilogram the data. When we talk about distributed optical fiber sensor.
Okay, so a lot of processing in this case. No?
Yes.
Using machine learning, artificial intelligence, no?
Yes.
And because there are a lot of, as you said, kilograms of data.
Kilograms of data, yes.
A bunch of data. This is a trending topic today in photonics, right? They apply machine learning, deep learning techniques in order to obtain and to process and having everything okay, right? Well, I don't think it's enough time for this talk, so let's say that we can continue in the coffee break. And let's start, let's thank the speaker again. And